Hello everybody. Today we are going to discuss about the structural analysis of simple truss. Okay, truss are kind of structural members. Like there are a lot of small elements attached to it, and then usually we use that one for support heavy loading system. You can see a lot of trusses in the roof of your building, which looks like something like this. These are usually for uh, residential building. These are made of wood, and for bridge trusses, you can see when the span is too big, then basically the load coming to that truss is huge. So usually we use truss. Okay. Now, what is simple truss? This means like when we are gonna analyze that uh, truss, then basically we are assuming two, like assumptions. The first assumption would be that all the loads are actually working at the joint, okay? Either here or here or here at the joint, okay? That's the first assumption. And the second assumption is all the members are joined with a pin, okay? So which means like basically all the joints are working here and they are kind of intersecting in a particular point, so that we can consider that one as a point or a node or a particle, okay? So that we can say that summation of fx and summation of fy at that particular point is basically 0. Okay, there is other reason that we are assuming that why the connections are actually pin connected means like if you have two pins in any rigid member, then basically we call that one link. And then if we cut a link, then basically we can show that one with one force that's working along the longitudinal axis of that particular member. Okay. So the number of unknown will be less here for that assumption, okay? For a general case, if you cut a rigid member, there will be 3 component of reaction. You already know that one, right? One is longitudinal force, the other one is shear force, and the third one is bending moment. But because of that assumption, we are considering here that both sides are pinned, then basically if we cut a member, then only we can see the force working along the member of that axis. Okay, it could be either tension or compression. At the beginning we don't know, but we can assume either tension or compression at the beginning, and if we get a negative number, then basically this one would be the other one, what you assumed, okay? Now let me show you what is actually compression and what is tension. Let's say if I cut a section here, let's say, then I can show that one equal opposite. Let's say this is P here. Now if you look at this one, then basically you can see that P is actually pulling away from the joint, okay? So P is basically tension here. Same thing if you look at here, then basically you can see this force is pulling away from the joint. So we have to very concentrated at the node at which this point is working, okay? So take a look at that particular joint and try to see whether this one is going away from that joint or going towards that point. If it goes towards that point, then it's compression. If it goes away from that joint, then basically this one is tension. Let's say here, if I cut a section here, and I can show 2 different forces here. Let's say this is R. And if you consider this force R, then you can see this one is going towards the joint, okay? It was going towards the joint. If it goes towards the joint, this means like this one is compression. So the same force, if you look at here, then actually you can see this one is going to that particular joint, like which this one is connected with. Okay, so basically this one is compression. So a member of the truss would be either tension or compression. Okay, now we are going to talk about two different types of methods here. The first one is joint method, and the second one is section method. Okay, so for now I'm going to discuss about the joint method. Okay, so in that particular method we usually assume that since whole truss is in equilibrium, so every joint of the truss is also in equilibrium. Okay. So now I am going to show you some of the examples from the joint method. Okay, now I'm going to show you example, the problem 6-3 in your book. Okay, this one is showing here that you have a support system here, rollers here, and a load 130 pounds is working at point A, and you have to find out the internal reaction for all the members here, that how much load is working there. You can see that if there is no external load here, then basically there won't be any internal loading here. Okay, but if you want to see the internal loading, then basically you have to make an imaginary card there and try to see that what type of forces is working there. Okay, so let's say for this particular problem, since we are following the joint method, we'll just try to see that which joint we are gonna start first. Okay, since for equilibrium for a particle, we have two equations like summation of fx and summation of fy, so we can handle only two unknowns. Okay, so we have to take a look all those joints here, that is there any joint there which has only two unknowns. Okay, if we don't have that one, then basically we have to find out the reaction here and there and try to see that whether we can start from that point. Actually, you will see these are all simple, like trusses, which is given in your chapter, in all the problems in this chapter. So you will be fine to find out either a joint which has two unknowns, or you have to find out the reaction first, and then you will see that there would be some joints which has two unknowns here. Now if I take a look here, then I can see at point A, I have two members here, so these are two unknowns here, right? So I can use summation of fx and summation of fy and find out what would be the force working at AC and what is the force working at AB. Okay, so I don't need to find out the reaction at E or F here. Okay, now let's start with joint A. If I draw that joint here, this one looks like this. This is my joint A. I'll show that one as, let's say, I don't know whether this is tension or compression, but at the beginning I'm just assuming this one is tension. If I get a negative number, then basically this one would be compression, right? Similarly, I'm assuming this one is compression. So this one is F, AC, and this one is F, AB. If I dissolve that force into two components here, then basically you can see the force in this direction would be 12 13th of 130, which is actually 120. And this way is 5/13 of 130, so which is 50 pounds. Okay, now for this particular joint, since this one is in equilibrium, then I can write the equation for equilibrium. Okay, so let's say start with summation of Fy equal to 0. Let's upward is positive. Then you can see also here that this is 4 and this is 3. So if I show that one here, this is 4, this is 3, so this one would be 5. Okay, you can find out the angle and use the angle too rather than the ratio. Okay, so you can see here that 4/5 of FAC minus 120 is equal to 0. So FAC that's actually 150 pound. And since I got that one positive number, so my assumption that this one is going towards that joint A means like this is compression, that's actually true. Okay, so I don't have to change anything here. Now if I do the summation of Fx here, let's say this is positive, so you can see for this one is like FAB minus 3/5 of FAC minus 50 is equal to 0. So FAB is equal to 50 plus 3/5 of FAC equal to 150, which is 140 pounds. And so once again you see that I got a positive number, which means like my assumption here, like that this one is tension, is valid. Okay, so I don't have to do anything there. Okay, now if I show that one here, so you can see this is tension, this is tension, this is compression here, this is compression here. Okay, so this is 150 and this is 140 pounds here. Now once I know the force working here and here, I have to go to the next joint. Now which next joint we can go? You can see if I move from A to C, then basically I know AC, but this one, and this one would be unknown. So there would be 3 unknowns there. But I cannot handle more than 2 unknowns at a time. Okay, so I better go to joint B because I know this one and I can find out this one and this one easily. Okay, now let's move forward to joint B. So this is your joint B, and this one is 140. Let's say this one is FBD, and this one is FBC. So if you take the summation of Fx here, then basically you can see your FBD minus 140 equal to 0. So your FBD must have to 140 pounds, right? If you have 140 pounds this way, you must have to have 140 pound in the other way, so that the, like the particle is in equilibrium, right? Similarly, you can see, so this one is also tension. And if you take the summation of Fy equal to 0, then basically you can see FBC is equal to 0 because there is no other force here. Okay, so this one doesn't have any force here. So I can show that one here. And this one is basically 0. Okay, now you can see like how we can move forward from there. If I go from B to D, then I know this one, but I don't know this, and this. 3 unknowns here. But if I go to C, I know this is 0, this one is 150, and this 2 is unknown. So I'll be able to find out that 2 there. Okay, so let's move forward to joint number C. This is basically 0. I can take that one or not. That's up to you. Okay, so I know this one is compression 150. You see this one is going towards the joint, so this is compression, right? If you make a mistake here, like if you show that one a tension here, then basically your whole problem whole solution will be kind of a mess up, okay? So very careful about that. So that's your point C here. Now let's say this is your force FCE. Let's say this is FCD, and you already know this one, right? And you can see this one is 3, 4, 5. Similarly, this one is also okay. Now you can see I can just take the summation of forces in x and y direction. Let's say I'm assuming summation of Fy equal to 0. Then you can see this one is going downward, this one is going upward, so upward is positive. 4/5 of FCD minus 4/5 of 150 is equal to 0. So FCD is equal to 150 pounds. And again, I got a positive number. So the assumption that this one is tension is valid. So if I show that one here, then I have to show that one as a tension here. Okay, this one is pulling that joint here, this one is pulling this joint here, and which is 150 pounds. Now if you take the summation of fx, then basically you'll be able to find out this force here. Okay, so let's say summation of fx equal to 0. So this one is 3/5 of FCD plus 3/5 of this 150 minus FCE is equal to 0. We know that FCD is also 150, so I can just put that 150. So FCE would be 180 pounds. Okay, so this one is basically compression. Okay, now I know this one and this one, then basically I can go to D and easily find out this one and this one here, right? Okay, let's go to joint D here. Okay, you can see this is my joint D. So you have one force working here, 140 pound, and then you have FDF, which is here. Okay, I don't know the value here though. And then I have this force here, which is basically FDE, and then I have one force, 150 pounds here. Okay, now you can just find out the forces FD and FDF from there. Let's say summation of Fy equal to 0. So you can see FDE minus 4/5 of 150 is equal to 0. So FDE is equal to 120. Okay, now I can take the summation of Fx and find out the FDF. FDF minus 140 minus 3/5 of 150, that's equal to 0. So FDF is basically 230 points here. Okay, so you can see again, like I got like positive number here and positive number here, so my numbers are fine. Means like my assumptions are okay. So this one is compression and this one is tension and this one is 230. Now you can come to E, and I have a reaction here and this force EF, and I can easily solve that one. Okay, now let's go to point E. This is your reaction because this is a roller, so this, you have only one component and that's working vertically. So that's the reaction at E. You know this is 180. You already know this one is 120. And this one, I assume this one is REF. EF, and you know this angle here is 435. Okay, now if you take the summation of fx, so you can see 180 minus 3/5 of FEF is equal to 0. So FEF is equal to 180 into 5 divided by 3. So this one is 300 pounds. Okay, so this one is basically 300 pounds and compression. Okay. So that's the way we do like the joint method. We just move from one joint to another joint. And how do you go there? We just try to see that which joint has 2 or less number of unknowns there. Okay, if the number of unknowns are more than 2, then basically we won't be able to solve that one using this joint method, because we have only 2 equations for the equilibrium of a particle. Okay, now you can see most of the time in this problem, actually when I'm assuming the direction, that was correct. That's because of my experience for so many years that I can see the joint and I can understand which way the reaction is going to go, so that the joint would be in equilibrium. But that might take a little bit time for you, so you just assume anything at the beginning and then change that one as soon as you get a negative result. Okay, now let's move forward. Problem number 6-10. You can see here is the truss. We have one pin support here and a roller support here, and 2 loads are working, 6 kilonewton and 9 kilonewton. You have to find out the force working along the members of that truss. Now the first thing what we have to do for the joint method, we will search that is there any point which has only or less or equal to 2 unknowns here. So if you check everywhere, you can see the number of unknowns is 3, 3, 3, 4, and 4 here. Okay, so you cannot find out any point. So what we have to do, we have to find out the reaction there, so that if I know that reaction here, there will be only 2 unknowns here. And if I can find out the reaction here, like 2 reactions here, then basically I'll find out easily this one and this one. And then we can move forward, right? So to find out the reactions here, so I'll just show that one as a force. let's say this is FD, this is, let's say, AY, and this is AX. Okay, so the pin we have two unknowns, right? Two reaction, component of reaction is two, vertical and horizontal, and for the roller you have one here. Now if you take a moment at point A, so summation of point, let's say counterclockwise is positive, then basically you can see FD into 12 minus 6 into 4 minus 9 into 8 is equal to 0. Okay? So you can see your FD is equal to that's actually 8 kilonewton. Okay? If you take the summation of Fx for the whole truss, then basically you can see Ax is equal to 0. Okay? And if you take the summation of Fy is equal to 0, then you can see Ay minus 6 minus 9 plus 8 is equal to 0. So Ay is equal to 7 kilonewton. Okay? So now I can show that one here, which is actually eight kilonewton here, and Ay is 7 kilonewton, and Ax is basically 0, so I'm not going to show that one here anymore. Now you can see that at point D I have two unknown, at the same time point A I have two unknown. So I can start either with A or from D, right? So before going there, let me find out the angles here. So you can see from here to here is 12, so this one is 6 and this one is 6. So this angle is tan inverse 6 by 6, so is 45 degree. Okay? Similarly, this angle you can see this is 2 and this is 6, tan inverse 6 by 2. Okay? So let's say this is phi. So phi is equal to tan inverse 71.57 degrees. Okay, so this one is 71.57 degrees. Okay, now let's try to go like either A or D. I'll start with A. Okay, you can start with D too. Okay, so this is my joint A. You can see this is my 7 kilonewton here. A force is working FAE and a force AB, and you can see this angle is 45 degree, 45 degree, 45 degree, 71 and 71 here. Okay, so you can just try to see that summation of, let's say, Fy equal to 0. then you can see 7 minus FAE sine 45 is equal to 0. So FAE is equal to 7 divided by sine 45, which is actually 9.9 kilonewton. Since this is a positive number, and I assume that one is compression, so you can just write that one as compression here. Okay? Now let's take a summation of force in the x direction. So you can see FAB minus FAE cosine 45 is equal to 0. So FAB is equal to FAE that's actually 7 kilonewton. And you can see this one is pulling away from this joint. So this one is basically tension. Okay? And I can show that one here in future reference, that this one is compression and this one is tension. Okay? And you can see this one is 7 and this is 9.9 kilonewton. Now you can move like forward here because this is like two unknowns, but I'll just try to do that one first because I already know the force working down there and there is only two unknowns. Okay, so let's move to the joint D. Okay, now let's go to point D here. You can see that's 8 kilonewton is working this way, and there is a force coming down FDE, and this angle is 45, and there is a horizontal force working from D to C, so that's FCD. Okay, now if you similar to point A, if you just do the summation of Fy equal to 0, upward is positive, so 8 kilonewton minus FDE sine 45, so FDE that's actually 11.3 kilonewton. And once again, you can just do the summation of Fx here. So you can see FDE cosine 45 minus FCD equal to 0, so FCD is basically 8 kilonewton. And again, I got positive numbers, so basically this one is tension and this one is compression. Okay, so I can show that one here too. It's tension and this is 8 kilonewton. And this one is 11.3 kilonewton compression. okay? Now either you can go here or you can go here, that's up to you. Let's try to see point B. Okay, so here is your joint B. That's B. We already know this force is 7 kilonewton tension. There is an external load here which is 6 kilonewton, and there is a force here and a force here which is FBC and FBE. Okay, so if you take the summation of forces at point B, the summation of forces in y direction so you can see FBE sine 71.57 minus 6 is equal to 0. So FBE that's actually 6.62. kilonewton. Okay, similarly, if you do that one, like summation of forces in the x direction, so you can see FBC minus FBE, no, actually plus, right? Both of them is going the right way, right side. So FBE cosine 71.57 minus 7 is equal to 0. So FBC is equal to 7 minus 6.32 cosine 71.57. That's basically 5 kilonewton. Now we can move to C and we can find out this force here. Okay, so here is your joint C, and you can see here, that's your C, and you can see this is the force we have to find out, and we already know this one 5 kilonewton this way and 8 kilonewton this way. And if you take the summation of forces in the y direction, so you can see FCE sine 71.57 minus 9 is equal to 0. So FCE is basically 9.49 kilonewton, and then there's basically this one is in tension because it's going away from the joint. Okay, so that's the way you have to do that one. Now when you do by yourself, your sequence for joint could be a little different, but that's okay. You are going to get the same answer. Okay, let's move forward. Problem number 6-12. Okay, so you can see here, this is kind of a tower here. Both the support is hinge here and hinge here, and you can see 500-pound force is working at point C, another 500-pound is working at point D, and we have to find out the forces in each of the member of this truss. Okay, so the first thing is, like for the joint method, we have to find out from which joint we are going to start. Okay, so if I check here, then basically you will see that there is only one point D here which has two unknowns. Okay, so we have to start from point D. So this is your point or joint D is there, okay? So you can see there is a 500 force is working down there, and this is your FDC, and this is your FDE. Now we have to actually like find out the angles here before we go there. So you can see actually this DF is making like this angle here is basically tan inverse 3 divided by 12 or 12 divided by 3. That's actually 75.96 degree. Similarly, you can find out this angle here or this angle here. So you can see that the vertical distance from here to here is 6, and this distance from here to here is 6, but if you take like that 1.5 off from there, because this is 1.5 at the middle, then basically you will see this one would be tan inverse 6 divided by 4.5, which is basically 53.13 degrees. We don't need that one right now, but just for future use, I'm gonna keep that one there. Okay. Now, if you take the summation of forces in x and y direction, then basically you will be able to find out this force FD and FCD. Okay, so summation of Fy equal to 0. So you can see FDE sine 75.96 degree minus 500 is equal to 0. So FDE is equal to 500 divided by sine 75.96. That's actually 15.4 pounds here. Okay, and since this is positive and I assume that DE is compression, so this one is compressive force. Okay. Now if you take the summation of forces in x direction, let's say this one is positive, so you can see minus FCD minus FDE cosine 75.96 is equal to 0. So FCD is equal to negative 115 pounds. No, actually 125 pounds. So once you get that one negative, what does it mean? That means like that direction is wrong. It has to be the other way around. So if this goes like this towards this joint, then basically it's a compression. So I can take that one here and just write that one compression here. Okay. So we got the force in two members like here and here. Okay. Now I have to move to the next one. If I know this one and this one, then I can go here, right? At point C, and I can find out the force there. So let's move forward to joint C. Okay, so here is our point C, and you can see this 500 force is working here, and a compression of 125 pounds. That's what we found out for this member here, and this one is working here, which is 75.96, what we find out here, right? Because this is symmetric, so if this is 75, that side has to be also 75.96 degree. And then I'm using this angle is equal to this angle, so this is 53.13 degrees. Okay, so solving that one would be a little bit difficult here, but we have to follow the same rule though, like the summation of fx and summation of fy here, right? Because I have two unknowns. That's one is fcb, and this one is fce. Okay, so if I write the summation of forces in the x direction, then basically fcb cosine 75.96 minus fce cosine 53.13 minus 125 is equal to 0. Okay, now if I divide everything with cosine 53.13, then basically you will get fce equal to cosine 75.96 divided by cosine 53.13 fcb, and minus 125 divided by cosine 53.13. So this one is fce is equal to 0.404 fcb minus 208.33. That's equation number 1. Okay, so similarly we can just write the summation of forces in y direction. Let's say here upward is positive, so fce sine 53.13 plus fcb sine 75.96 minus 500 is equal to 0. So again, if you express that one in terms of fce by dividing all the factors with sine 53.13, then you get fce is equal to 625 minus 1.213 fcb. This is equation number 2. So if you subtract 2 from 1, so you just put that one here, fce is actually 625, and this one is 1.213 FCB. Subtract that one from here, then you just get your 1.616 FCB equal to 833.33. So your FCB is equal to 515.4 pounds. Now if you plug that value FCB in either equation 1 or 2, then you get your FCE, and you will get 0 there. Okay, so actually there is no force working in this particular member. Okay, so this one is actually 0 force member. So you can remember this one is compression 125, this one is 515 compression 0.4 pounds, this one is also 515.4, and that's also compression. Okay, now we have to move to the next one. I know this one and this one, I have two unknowns here, so I move to joint E. Okay, so here is your point E. You can see this is your compressive force working down here is 515.4, and there is this force like FCE, which is 0, so I don't want to show that one here just for clarity. Okay, and then I have one force FB here and FEF here. Okay, so if you see, actually the angle here and angle here is 75.96 degree. Okay, so if you take the summation of forces in y direction, so you can see if EF sine 75.96 minus 515.4 sine 75.96 is equal to 0. So FEF is actually 515.4 pounds. Okay, now if we take the summation of forces in x direction, let's say this is positive, so 515.4, this one is going this way, cosine 75.96, and then this one is going like this way, negative 515.4 cosine 75.96 minus FBE equal to 0. But you can see this one is this one cancels because it's same quantity. So actually your FBE equal to 0. Okay, so this one here so this one is actually 0, and this one is actually 15.4. So I need like these two here, so I have to move in this point, okay, which is B, and then we have to solve that one, okay, to find out the other one. So this is your point B now, and you can see there is a compressive force working here, 515.4. I didn't show like BE because this is 0, okay, and then this one is FAB and FAF. Now you can do that one with like the same axis, like the universal axis, horizontal and vertical, but in that case this one would be much easier. Like if you take, this is your y bar axis and this is your x bar axis, okay. Why I'm saying that one, like you can see here easily that if you take the summation of force in x bar direction, let's say summation of forces in x bar direction, then you can see that minus f bf, whatever the angle here, cosine theta is equal to 0, so f bf is equal to 0, okay, FBF equal to 0. And if you take the summation of force along y direction, then you can see FAB would be same as 515.4, right? So here, if I take the summation of force into y direction, y bar direction, so you can see actually FAB minus 515.4 is equal to 0, so FAB is 515.4, and you can see this is positive number, and I assume this one is compressive, so this is a compression here, okay? So thank you for watching.